Okay, so we can start today's session. And if you attended the last session, we have been discussing about robot perception, specifically using ROS. So I hope you remember some things that we have discussed in the last class. Like we talked about the uh, objective of why RO is using for the perception of robot. Why and what is advantage that we are getting. So I talked about like RO is basically a message passing interface framework basically, but the advantage is that we can uh, isolate the hardware from the software. Like if there is a driver node which can publish the images, you can simply bag it and then we can use it for offline processing. Another advantage is that we can work on multiple programs from the same device. Okay, so these are some of the advantages, and we have talked about like OpenCV, then PCL. Okay, and the last topic that we have been discussing was ROS bridge. Okay, ROS bridge. Uh, it's also called the CV bridge. It's basically a package, and this package is having some nodes, so that is acting as the bridge. Okay, so why we are using this bridge? I think I have mentioned that yesterday. So basically, um, ROS is a message passing interface, message passing framework, and OpenCV is a computer vision library. So if we want to do the processing, we want the OpenCV, the image data in the OpenCV format or OpenCV data type. So which is CVMAT. It's not a data type. It's a class actually. Yeah. So basically, in OpenCV, we are using mat class in order to hold an image data. Like an image will have RGB layers and also some image having the alpha layer. So yeah, one second. Kasim, can you mute your mic?
Sure.
Kasim, maybe you can mute your mic. Um, just a second, guys. Okay, so so basically in the nodes we are doing processing using OpenCV, and after doing the processing we can send the processed image using ROS. So basically the ROS bridge, ROS CV bridge is acting between OpenCV and ROS. Okay, so the ROS image message, I think we have seen that yesterday. uh, we are in order to send an image between two nodes, so you can just compare the sensor message image is similar to standard message string. Like standard message string is a ROS message, right? So similar to that, there is another ROS message which is sensor message image. So you already know what is a publisher and subscriber. Like hello world, we already seen, right? So similar to that, we can send any kind of data. Like we can send point cloud, we can send image, whatever. Okay, so in order to send the image, it should be in the sensor message image type, and in order to process the image, it should be converted into OpenCV CVMAT. So the CV bridge is converting the OpenCV data type into ROS message and ROS message data type to OpenCV. Okay, so today I would like to start with a simple project. I think I have shown the demonstration of that yesterday. It's an edge detection program. Okay, so if you get an idea, then you can easily prototype other application. Okay, basically this application shows how to do the conversion from OpenCV to ROS and ROS to OpenCV. Okay, so that example is actually mentioned in the tutorial. Okay, so I have that code, and I can show you how to create a package and how to write a node. Okay, so this is a tutorial basically. Yeah. Yeah, so we are going to see this tutorial. Okay, so basically I have this package ready, which is in my workspace called Catkin workspace. So if you want to create a package, I think you already know, using Catkin create package you can create a new package. And in order to create a package like this, this is a package that we are talking about, okay, CV Bridge tutorial package, which is having the edge detection application. So just check the package.xml first, so you can see the dependencies. So in order to write a CV Bridge based application, what we require is obviously the CV Bridge package, CV underscore bridge package. Then we need image transport package. Okay, so image transport package is optional, but that image transport package, if you just search, which is actually in the perception pipeline, if you just check image transport ROS, so you will get a package. So this package help you to publish an image. Okay, like you can compress the image if you want to, if you don't want to send the raw image, you can compress it. Okay, so the image transport package is actually from the perception, from the ROS perception packages. One of the packages, image transport, which is using for subscribing and publishing image. Okay, so this package is giving us some functions. Okay, some functions for publishing and subscribing. Okay, so we can actually use symbol subscribe and publishing for image. That is actually possible, but the image transport can be used for like compression, or so it's more than just publishing. Okay, because like if you are working with string, or if you are working with integer, it's the bandwidth of these data is very less, right? I'm not sure you remember how this exchange of data between two nodes are happening. Basically, like imagine if there is a talker and there is a listener. Okay, so talker is publishing the data, okay, keep on publishing the data, and listener is like subscribing. And talker doesn't know about listener doesn't know about talker. Only the topic name only matters actually. And whenever there is a match in the topic name, then master will be like get connected with these nodes. Okay, so this is what happening underlying. So in order to send, before sending the data, it should be serialized. Okay, serialized means we can't send an image at once. We have to serialize the data. The data is going through in a serialized manner. So if it is a string, if it is an integer, it's very easy to serialize and deserialize. Okay, so it's like maybe I can just compare, like if you send a hello world, then it is actually flowing through like in a tunnel. So it's like H will go first, then E will go second, L will go third, like that. So the hello world will be going one by one, H, E, L, L, O, W, O, R, L, D, something like that. So if you are sending an image, then what will happen is we have to serialize the entire image and deserialize it in the subscriber side. Same for the point cloud. So the problem is that if you are sending an image, the serialization process is happening, and obviously it will consume CPU, right? And the same thing happen for the deserialization. Okay, so if you're sending images like to 5 or 6 nodes, it will consume a lot of CPU only for like sending the data, okay, publishing and subscribing the data. So if you want to optimize the bandwidth, okay, so we are sending the data between these programs, right? So even if we send the data between programs from the same system or some different system, obviously anyway it will consume bandwidth, okay, and it will consume CPU. So this image transport, no, it is actually an optimized method to send and receive the images. Like it's same as the publisher and subscriber, but in a better way. Okay, so that is the image transport. Okay, so you can send or publish the images and subscribe to it. Okay, so you can compress it. Okay, so that will not take much CPU. Okay, so we will see that. So image transport. So whenever you are planning to send an image, I will prefer to use the image transport package in order to publish and subscribe. Then the ROS CPP, we are going to see a C++ example, and we need the sensor messages as a dependency. So why we need? Because we are using image message from the sensor messages. Okay, and also we may need standard messages. It depends on your application. If you are using standard message something, then you can include it. Okay, so these are the build dependency. Build dependency means in order to build this package, we need these dependent packages. Like in order to build the package called CV Bridge tutorial package, we need to include what? We need to include these build dependent packages. Okay, and in order to run the node, we need this package, almost the same package. Okay, so sometime the build dependent package and run dependent package can differ. Okay, so this is the package.xml. So when you create the package, just include, like you can use the catkin create package, right? Catkin create package, then CV bridge tutorial, then just start including the dependency. Okay, ROS CPP, send some messages. I mean, you can include everything and create your own package. Okay, after creating the package, what you have to do is you have to edit the CMake list. So the default CMake list is like a mess because there are a lot of comments and it's a big CMake list, but you have to clean it. Okay, you can include only the macros that we are using. So if you check the CMake list, you can find it's very simple. Like it is having the minimum version of CMake, then the project name basically the package name, and the packages we require. Okay, that will be automatically coming, and then find package. Okay, so if you are working with OpenCV application, it will be good to include the find package OpenCV. Sometime it will be working without this line. Even the CV bridge is depending on OpenCV, but it will be better to add this one. Okay, so this will be like this will be including the OpenCV library as a whole. Okay, and then like in the include directory, okay, it is including the OpenCV include headers. Okay, it's including the headers from OpenCV library, and in this package there is one node. Okay, there is only one node which is called sample CV bridge node.cpp. So this is how we can build it. Okay, so I think this is familiar to you, right? Using add executable. This is executable name and this is the CPP file. So if you check the SRC folder, you can find the CPP. So you can put your code inside the src folder, and then you can add these line in order to compile, because CPP code has to compile. If you are using Python, you don't need to. Okay, so this same thing work with Python as well. Okay, but I will prefer C++ because in this kind of high bandwidth application, C++ is doing better job compared to Python. Okay, in the memory handling and all, C++ is doing better job. Python for quick prototyping, it's okay, but the bottlenecks comes when you work with embedded system. For example, currently I am working with a client, so they are using Jetson Nano, okay, in the robot. The bottleneck is the RAM. So like you all are going to work with robots, right? So some point of time you have to use like some embedded boards like Nano, Savior, I mean some kind of embedded device, and then the resource may be limited. Resource in the sense CPU and the RAM. So if you are using a lot of Python nodes, it will consume RAM, and the robot may not work properly after some time. So that can happen. So it's our duty to write optimized code in order to not use the complete RAM, because if you are running nodes which is consuming like 3.8 GB out of 4, and you are trying to run the robot, or you are trying to like operate the robot, after some time there can be some issues. Okay, because the robot is continuously working and this RAM usage can accumulate. Okay, so it's very important to create optimized programs, but initially maybe we can't able to create a optimized program for the robot, but gradually you have to keep on modifying your code to consume less RAM and less CPU. Okay, it's all depend on your logic. Logic can play a big role in optimizing the code. Optimizing means there are a lot of levels in optimization, I think. Like if you change the logic, okay, if you change the logic, you can save maybe memory, and if you use some functions, okay, for example, in order to write image or in order to read image, if you use some functions, it will consume less CPU. Okay, so these kind of things will comes only when we are out of RAM. Okay, the memory is the biggest constraint. CPU, I will say CPU is also a constraint, but if you are using Jetson series, and if you are using like some kind of deep learning, for example, a lot of processing can be diverted into the GPU. Okay, but CPU again a bottleneck. Like if you are working with the navigation, mostly like we are most of the company are working on indoor robots, outdoor robots, mostly like navigation, autonomous navigation. So if you want to work with the navigation stack, it will consume only CPU. It's not GPU accelerated. So yeah, so we have to optimize everything. That's what I want to say. So CPP is a good choice even for ROS 2. ROS 2, currently I'm working on a big project. It's completely using ROS 2 CPP. Even I am learning a lot of things in ROS 2 now. Like we have to it is having a lot of features, but mostly like if you're planning to do some big projects which need big performance, good performance, I will prefer CPP. Okay, so this is a CMake list, so you can use this as a template. Okay, this I will be updating this package in Git, and then now we can have a look onto the C++ node. Okay, so don't worry about the line of codes. The logic is very easy. Okay, the logic is very simple. It's basically, you know, the logic I can just show you in a PowerPoint. Okay, So we have the node. So what it does is that oh, just a sec. The node will be subscribing. This is a node, okay, and the node will be subscribing an image. Okay, and then node will do some processing, edge detection. Okay, the node subscribes and then do edge detection, and then after doing the edge detection, it will publish the processed image. Okay, so this is happening inside the entire node. Okay, so maybe I can remove this process image. So basically node will subscribe to an image, process image, publish image. Okay, so this is what happened in the in this code. Okay, and so I think I have shown you how to write a node, ROS C++ node using class. Okay, this is very useful way of writing nodes even for ROS too. So if you just check ROS CPP class, CPP node class template. Okay. Okay. Yeah, maybe example is difficult to explain anyway. So I think you have seen the publisher and subscriber node, right? So in that it's very simple. Like inside the main function, we are like creating the publisher and keep on publishing. Okay, but if you are creating a big project, I will prefer you to start with a class. Okay, start with a class. I mean node with a class. Okay, the advantage is that if you're creating a node and if it is a big project, you may need to include many functions. Okay, many functions. So class can I mean it can include lot of functions in a better way, right? So here what happening is that they actually created a class called edge detector, and inside that they are like creating subscriber and publisher. So subscriber will be subscribing to an image from the driver. Okay, USB cam. Okay, so if you are like publishing an image in this topic, this node will be subscribing and then doing the processing and then publishing in to this topic. Okay, so in this class the name is edge detector, and these all are like the class I mean the objects inside the class for node handle and then for publishing and subscribing. So you can understand the image transport. We already discussed about the image transport, right? So we are using image transport here for publishing and subscribing. So this is that image transport API. I will explain it, and this is the constructor of the class. Okay, this is a constructor of the class, and this is the destructor of the class, and this is the callback. Okay, this is the callback. Okay, and this is another functions for detecting the edges. Okay, so what is happening is that whenever there is an image comes to this topic, okay, it will call to the callback. I mean, you know how the subscriber works, right? It will call a callback. So that callback is actually inside this class. Okay, so that callback is called image CB, which is inside the edge detector. So if the callback is inside your class, then this is how we are addressing the callback. Okay, so maybe I can show you the difference between this and the callback that we have discussed in the listener. So this is how we are mentioning a callback in the listener, right? Just mention the function name. But this function now, this callback is a like a global function, so we can simply mention the callback name. But if it is inside a class, then what you have to do is you have to pass the pointer like edge detector, which is the this is the address sign followed by the class name double colon image CB. Okay, and you have to mention this is actually a keyword which indicates the function is inside. Okay, so this is the modification we have to do in order to subscribe, and if the callback is inside the class, we have to use this kind of thing. Okay, so whenever an input image comes to this topic, it will call the image callback, which is this. Okay, so what is the kind of message type that we are receiving? It's the sensor message image. Okay, and here, you know, the image is actually it actually takes a lot of bandwidth, right? So basically we are not doing a copy operation. Instead of that, we are using addressing, like we are actually copying its pointer. Okay, so like the image comes and then we are not creating a copy, we are actually taking its pointer. Okay, so you may have seen the use of constant pointer address, and in some in listener.cpp also you have seen the constant pointer, right? So okay, I think there is a question, just a second. Yeah, so yeah, I can explain, just a second. So there are two address usage comes here. So the objective of this usage and this usage is that it's actually pointing to it's actually the pointer. Okay, like for the image callback, what happening is that when the image receive or when the image subscribe, if we are not using this constant pointer, we are getting a copy of the image message in this MSC variable copy. Okay, but this constant pointer, if we are using it, we are not creating the copy. We are not creating the copy, but we are using the original received image. Okay, so if you are using constant pointer, it can save the memory. Okay, but if you are not using the constant pointer, the memory can be doubled. Okay, because there is a received image and we are creating a copy of it. Okay, so that's why we are using this notation for addressing the memory of the received image. Okay, and this is also indicates like this is also like pointing to the function, to the callback. So this is the usage actually. Okay, so this is actually the usage when we use a callback inside from inside a class. Okay. Okay, so there is a question from Tejas: is image constant point is a part of API? Yes. So maybe I can show you that. So you have seen the sensor message image. Yeah, maybe I can show you that. Actually, Yeah, let me take the header file, then only I think that will be clear to you. Let me take some message header file. Let me just a second. Include, yeah, I think this can be an example. So I'm not sure you remember creating custom ROS messages. Like we can create our own message and then we are using that message. So what happening is that, like, this is a demo message. Okay, this is a demo message. Maybe just a second. I can show you the package, mastering ROS demo package. So this is what I'm talking about. We can create our own ROS message, right? So this is the ROS message, okay, that we have created. Okay, so once we do once we create this message and when we build the package, what happening is that it will build the message file and create a header file. Okay, header file, and this is where the header file comes. Okay, in devel include in the name of that package. Okay, so if you open the demo message.h, in every ROS message it's like that. Okay, you will get some already built ROS messages like sensor messages or standard messages already built. Okay, these header files are already included in the ROS installation. Okay, but if you create a custom message and if you build, you can get the automatically generated header file. And if you see, we can check what are the different type of usage for accessing that message. Okay, you can see demo message constant pointer, demo message pointer, and demo message. Okay, you can see the constant pointer. So if you are using any message, this usage, like the message name constant pointer is actually inside this header file. Okay, it will be automatically generated. Okay, so if you are using int, then you can do like int constant pointer. Okay, if you are using string, then string constant pointer, like this. Okay, so this is like this is actually a fixed thing in any ROS message. Okay, it is for accessing the data, the received data actually. Okay, we are not creating a copy, but it's actually pointing to the received data. Okay, so this constant pointer, we can use it, or you can simply use like this. Okay, so if you are using like this, you have to remove this as well. So this will be creating a copy of the received message. It will create more, it will take more RAM, but if you don't want to create that, then the constant pointer method will be good. So that is, if you search for any message header file, you can find the constant pointer. Okay, so this is how it is working. Okay, and so we have included the sensor messages header file. Okay, so this will have that this kind of header file. Okay, so this is for the demo message, and this kind of header file will be available in the ROS installation. Okay, for standard message, for sensor message, this header file will be there, and this constant pointer usage will be the same for all the messages. Okay, yes, I hope that you got an idea, Tejas. If you have any doubt, let me know. So so we have used a constant pointer, and then we got the pointer address, and now this section is the main part. Okay, this section is the main part. So what is happening is that this is the code which is converting the received message, received image message, which is in sensor message image type, okay, which is in the ROS image type. We have to convert to what? We have to convert into OpenCV, okay. Then only we can do the processing, right? We have to do the edge processing, edge detection. So what we are doing is, here we are trying to convert the received image into OpenCV data type, okay, OpenCV data type. So what we are doing here is we are creating a pointer, okay, from so there is actually a class called CV image pointer, which helps you to store the it can carry an OpenCV equivalent data type. So like the objective is that we are converting the ROS message into OpenCV, and we have to keep that converted image in somewhere, right? So that's where the CV image pointer comes, okay. So here this function, okay, inside the CV bridge package, there is a function called toCVCopy, okay, toCVCopy. So this function is basically converting the ROS message into OpenCV, okay. So you can see, like, this is the received message pointer and this is the image encoding, okay. So we are using image encoding BGR8, okay. BGR means blue, green, red, 8-bit, okay. Sometime it will change based on your image type. So this is the default one, okay. It will work in most cases. And so this line now, this line is doing the conversion from ROS to OpenCV, okay. And in the CV pointer, it will get the pointer for the OpenCV image, okay. It's already converted, and the CV pointer hold the pointer to the OpenCV image. And then what happened? Then using this CV pointer, we are actually passing the CV pointer to the next function. Not only to the CV pointer slash hyphen. This is the pointer. This is how we are addressing the pointer. Method. Not only method. The data inside the pointer. Like the CV pointer is this, okay, which is having the type of CV image pointer. And if we want the OpenCV image, we have to use like this, okay. So what it does is that from the CV image pointer, take the image, okay. So if you have confusion, just search for CV image pointer. So it will help you. It will come up with the things inside that. Just a second. So to this function, to detect edges, it is passing the CV image, okay, CV mat image. So just a second, I just want to show you this class called CV image pointer, CV bridge, CV image PTR. Okay, so sorry for the interruption. Yeah, so we have been talking about the CV bridge CV PTR. So basically this is a CV bridge.cpp, okay. So if you just search CV image PTR, CV image PTR, oh, I think it's in the header file. Yeah, this one. you can see this. So this is a function that we are using, and yeah, so basically the CV image PTR is a boost function, like make shared of the CV image. So basically I just want to like mention, like, this CVPTR can hold the OpenCV image. Okay, OpenCV image, not only OpenCV image, but the details of the image. Okay, some other aspect of the image. So here, in order to access the OpenCV image from the CVPTR, you can use CVPTR and the addressing sign image. Okay, so this is the OpenCV image. Okay, and so we are basically passing the OpenCV image to a function called detect edges. Okay, and in this detect edges, what is the argument? It's CV mat image. So you got an idea, right? This is a CV mat data type. Okay, so what will be the IMG? IMG will be the received image in OpenCV data type. And after getting the input image into this function, it is doing the edge detection. Okay, it is doing the edge detection. The routine, the function routine is for doing the edge detection. Okay, so in OpenCV, if you don't know about OpenCV, this is advantage. Like, if you get an image, you can do the pre-processing. This is actually converting the color image to grayscale. So we have a function called CVT color, so which is converting the input image, which is a color image, into a gray image. Okay, gray image. And after converting into the gray image, so currently the output is SRC gray. We are like doing some blurring. Okay, so this is all pre-processing for doing the canny edge detection. So there are some edge detection algorithms available. So like, if you search for canny edge, if you already learned about computer vision algorithms, I think you may heard about canny edge detection, which is one of the algorithm, classic algorithm for detecting edges. So we have converted to gray, then we have blurred the image for some size, and then we did the canny. Okay, so here the image called detected image, okay, image variable called detected image is holding the detected image, sorry, the edge detection image. Okay, so after doing the canny edge detection, we are copying this image into a another image called DST. Okay, yeah, it's copied to, okay, it seems like the edge detection image will only have the edges. Okay, so that edges will be copying to the image. Okay, so the color image will have the edges, but if you just view the canny edge detected image, it will be like black, and it will have the edges. But here we are doing like a copying operation. The edge detection will be copying to the color image. So I think you have seen the output. The detection is marking in a colored image. Okay, so that is happening in the detect images. Okay, okay. So after converting the received image to edge detection image, what we are doing is we are publishing the converted image into ROS message type. Okay, so here you can see the CVPTR to image message. Okay, so what happening is that we are actually editing or we are actually modifying the received or the original image, right? So if you do any processing, it will be happening in the original image. Okay, so if you do the detect and everything, if you modify, it is actually modifying the original image. So the CVPTR, after these detect edges, the CVPTR will have the edited image or the edge detected image. And the CVPTR is actually the class, right? It's a CV image PTR, it's a class which is having a function called toImageMessage. Okay, so that function will be converting the final image into ROS message. Okay, and you can able to publish it. So if you check the image pub, you can able to see the definition of it. Okay, so it is publishing to the edge detector raw image. Okay, so initially it may looks complicated, but it's not that much. Like if you check the main function, it's basically like simply creating an object and doing the row spin. Okay, uh, the confusion can happen in this conversion. Okay, the conversion, these two conversion. But if you're used to it, I mean, these things will be the same for all type of conversion. Okay, if you are creating any big programs, basically this line can be reused, these two lines. Okay, so like receiving the image, then converting that image into OpenCV data type, and then doing the processing. After doing the processing, publishing the image, publish the processed image. Okay, so maybe I can just run the node again, so you will get a clarity again. So we are starting the driver. So before starting the driver, what you have to do is you have to connect your webcam. Okay, so I am working from the VirtualBox or VMware. So I'm connecting my webcam to VMware. Just a second. And then you can check if your webcam is properly connected. In robot also, like using dmessage, DMESG, you can identify whether the camera is properly connected. If it is properly connected and properly registered, you will get some messages like this. Found UVC device. There are some errors, but I think mostly it will work. You can ignore this. Finally, you can check this message: USB core registered new interface driver UVC video. Okay, if you are getting this, then you are done. Okay, now you can start the driver. Okay, so the driver got just started. Okay, so the driver is running now, and now you can check the topics, by the way. So it is publishing a raw image in USB cam image raw, and there is a compressed image as well. Okay, so this is the advantage of using image transport. If you want to subscribe to an image from your robot, there are different topics. Okay, so imagine the robot is connected through a Wi-Fi network, and your laptop is also connected through Wi-Fi. Okay, so now there is a bandwidth problem, like the data has to flow through the Wi-Fi network. Okay, if it in your same system like this, then I mean it will be much faster. Okay, but if you are working in a network, then it will again delay. So at that situation, you can use the compressed image. Okay, so compressed image will not take much bandwidth. So there is a command to check that in ROS topic bandwidth. If you check the compressed image bandwidth, it is like 1.3 MB per second. Okay, and if you check the image raw bandwidth, you can check the bandwidth. It is like 22 MB per second. Okay, so just understand like how much bandwidth will be required to transmit an image through your Wi-Fi network. It's MB, not small b, it's MB. Okay, so this much processing also required. For example, if I'm using HTOP, oh, HTOP is not available. Just a second, let me install HTOP. HTOP is like a interactive process viewer. It will be helpful here. Just a second, let me just stop. Waiting. Oh, I hope you also get this error before. Let me, one of the fix is deleting this log. Okay. Oh, could not get the log. I don't know. Sudo rm. Let me delete. Okay. Yeah, it's working. So that is happening like if there is any log file or something. Yeah. Okay. Okay. Just wait for some time. So if you check the node, this node, so which are the area that takes computation when we subscribe to it. Okay, there is a serialization and deserialization is happening, and when we process the image, so that is using OpenCV, and when we publish it. Okay, so these are the three areas it is taking. So HTOP, I think you have used it. There are one more process viewer. If you are using Jetson board, there is a JTOP. It's very famous. It's actually done by one of my friend in Facebook. Yeah, we are in touch actually. Yeah. So yeah. So this is the memory consumption, 1.29 GB. So I'm starting the driver. Okay, so currently it is 1.43 GB. Okay, and if I am checking the bandwidth means we have to subscribe anyway. I mean, the ROS topic will be subscribing and then gauging the bandwidth. So if you do that, it's actually jumping. See, it's jumping to 1.46. Okay, so it was 1.43. Okay, so 43 means like 430. Okay, 430 MB or 420 MB. Okay, if you check the bandwidth of the raw image, it is 470. Okay, so just check the jump from 420 MB to 470, right? So it's like 500, like 22, yeah, 2 to 7. So it's like yeah, so it's actually very big, right? Like even it's like yeah, 420 to 470, so 50 MB maximum it's taking, right? 50 MB of RAM it is taking. But on the other hand, if you check the compressed, you can check, I think slightly less, like it is using 1.4546. so like it's showing 4647 sometime, but mostly like if you take the average, it is like 0.45. Okay, so that is actually the difference. Okay, and also the bandwidth is 1.2 MB. Okay, so that is the thing. Like if you engage in any activities, we don't actually care about the RAM because we are working from the laptop, and your laptop will have like 8 GB, 16 GB. But that is not the case if you are starting working with the robots. So now I am just starting the application, that is CV Bridge demo application. ROS launch CV bridge tutorial demo.launch. Okay, so now we can see the jump. So from 1.42 to 1.51 GB. Okay, so like 420 to 510. Okay, 420 to 510. It's like 60 MB of RAM. Okay, so you can see the edge detected image is actually copied to the colored image. That's why we are seeing like this. Otherwise, it will be simply black and only the edge detection will be there. Okay, yes. Okay, so this is happening, this much of consumption is happening only because we are processing the raw image. Okay, yes. So this is the output that we are getting. This is the raw image, and this is the edge detection image. So I mentioned right here, in these 3 lines, it's basically copying the edge detected image to the main image. Okay, so the thing is that if you plan to work with OpenCV, it's actually very easy. Just understand the input and output. That's it. Okay, so we can simply use these functions, and yeah, we can play with it. It's not a big deal. Okay, but if you have prior understanding of the algorithms, classical image processing algorithm, that will be a great help. Okay, and you can also check the CPU usage, like without the application, the CPU was about you can check like 6, 7. Yeah, the load average I think 0.97, and when you start the application, it's actually jammed. Oh, so it's like from 6 to 13. So all the cores are started to use 16, 14, something like that. Okay, so if you run like 4 application like this, then it will load the entire CPU. Got it? So yeah, so you should be careful while working with this kind of image processing, as well point cloud application in the robot. Okay, you can create your application in your workstation. Okay, you can create, but it's very difficult to deploy that in the robot which is running on an embedded system. Okay, so if you're working with Savior or like the latest one, I forgot the name, if you are using the supercomputer, it's actually very expensive. Just a second, Savior Jetson, which is very expensive. It's like 1 lakh. Yeah, but if your algorithm, yeah, Orin, thanks for the clarification, Trishant. So but we can actually minimize the cost of the device by optimizing your algorithm. I had an experience, small experience, like in the optimization side. So the Jetson Nano is actually cheap, but currently it's very difficult to get Jetson Nano. If you check in all website, it is out of stock. So we will be tempted to buy the Savior or Orin, which is the latest one, but it's very expensive. So imagine if you want to sell a robot in 3 lakh or 4 lakh, and if you want to sell that in that price, you have to be like, you have to make the robot within like 60,000 or maximum of 80,000, right? So how to make it? So if you make it, then the price of computer is coming, right? Price of computer. So if it is Nano, the actual range, the original price, like it is less than 10K. Okay, okay, it is okay, affordable. But if you are switching to Savior, in India, it is like, yeah, it's actually, yeah, it's pretty expensive. Okay, so it's taking like almost 3/4 of the robot cost. Okay, it's actually very good board, but it's too expensive. So in my experience, like there is a situation where we have to use people detection. Okay, people detection in the robot. So other than the navigation stack and the web interface, we have to use people detection. So the people detection you can easily prototype in the laptop. There are a lot of applications like deep learning based applications available in Python. But if you are going to deploy that in Nano, then it will eat all the CPU and RAM. Okay, it's actually very difficult, and we have to run this people detection along with navigation. Okay, so if you run ROS navigation stack with all the drivers, that itself take like 2 GB, 2 GB. And also the CPU, yeah, the Tejas, yeah, it's difficult to work with Jetson as it's ARM based, yeah, architecture based as well. Like it is having the ARM architecture, and some of the package may not work properly because mostly the ROS packages are designed for x86. Okay, currently a lot of conversions happening, but yeah, there is a problem like that. But again, if you're working with Jetson Nano with 4 GB, I mean, like if you run the simple navigation, it will take 2 GB or 2.2 GB of RAM. Okay, and also like 1/4 of the CPU. Okay, and when you run the people detection algorithm, then it's over, game over. Okay, it can't able to run. So there is ROS deep learning stack. Okay, ROS deep learning stack from NVIDIA, which is actually a very optimized package for Jetson Nano or Jetson series boards, which can run deep learning stuff very optimized way. Like it will be only using 1 GB of RAM, and for processing, 3/4 of the processing is doing by CUDA cores or the GPU, and the CPU usage is also not very high. So it will be around like 3 GB out of 4 GB. But again, that is critical. But what I'm trying to say is, like if you can find those kind of application, we can actually optimize the processing. Okay, but again, there is a lot of challenges. I have actually modified this package. Why? Because they are actually using streaming nodes for streaming each camera. I have to do people detection not only for one camera. I have to use 5 cameras. It's like 360-degree kind of arrangement. So around the robot, we have to put like around the robot there's totally 5 cameras, and we have to take input from 5 cameras. So again, we have to do it in Nano, but again, that is actually possible. So what I did was I actually used the USB cam. Okay, you know the USB cam package, right? So USB cam package is having a library as well. Okay, library in the sense it is having a class which can be used to read image from the webcam. So I have did a reading of the 5 cameras serially, like not reading the image simultaneously but in a serial manner. So it will not take much CPU. Okay, and this is actually feeding to the deep learning functions of the deep learning package from NVIDIA. So if I'm doing it separately, independent streaming, it will not be possible. So what I'm trying to say is there are many methods to optimize the computing resource. So you will be only aware of these kind of things once you start playing with navigation, then high-end stuff like navigation that include mapping, localization, perception. This is very difficult to handle. It's not easy as you think. So uh, Tejas is having a question: will the optimization be different in ROS 2? Yeah, so optimization is actually very deep term. Deep term in the sense, you have heard about the code optimization, and not only optimizing the code, but like I can explain a scenario. Uh, you are doing a people detection, like me, you are doing the people detection. So you have a code with a CNN based model, and you are optimizing that code. Okay, you are optimizing that code, but that is not the solution actually. You have to go with some framework which is optimized. Okay, so not only code optimization, but also choosing the right framework will be also helpful. Yeah, regarding the hardware acceleration, yeah, I am actually working with that hardware acceleration, guys. So there is an announcement coming in the ROS Con this year. So yeah, so I'm not releasing that now, but yeah, there is an announcement coming in the hardware acceleration community. Uh, so the hardware acceleration is a stack which can be used to accelerate the stuff using FPGA and all. So those can also like kind of optimization to improve the entire processing. Okay. Yeah. So I just mentioned about some practical stuff. It may be useful to you. It's actually out of scope, but it's actually very very useful when you start playing on the robots. Okay. So that is the CV bridge and the sample code. Okay. And you guys are like maybe planning for masters, or like maybe planning for to work with big companies. So at that time you are going to work with high-end stuff, like you are playing with lidar data, chunks of data, and you have to label it, you have to do the detection. So at that time you will get to know like how difficult to do this as well, optimize it. Okay. Yes, so that is the OpenCV thing. Like we have used ROS and OpenCV combination, and we also talked about the resource thing. So when we start discussing the next stuff, that is ROS and PCL, the things will go in another level, because the PCL ROS, instead of image, we are handling the 3D point cloud. Okay. Yeah, Trishant is having a question. Then, sir, what will be the proper flow when considering or in series or any constrained embedded device? Yeah, so Trishant, so choosing the right computer, it's actually even difficult for me. I mean, I'm not saying I am like know everything or something. I'm still learning. I'm still a student. But from my experience, what I learned was like one of the major constraint is the cost itself, because we can't include an Orin or Xavier board in a low cost robot. Okay, because in Indian market, if you are working with the Indian market, can we sell a indoor robot with like 20 lakh? I mean, I don't know like if there is a market for that, but obviously we are trying to reduce the cost, right? So if we don't have any option, then only we will think about expensive. So first think about like the boards that can able to work I mean that will work with our application, and after rigorous testing, uh, yeah, then only we can understand is that enough or not. Okay. So currently like for a client, we are again in a situation to choose uh, the computing board. Currently we are using Nano, and Nano is not available now, so we are thinking like switching to Xavier or Orin, but the the cost of the robot is not that much high. Okay. So I don't know, like there is Odroid, there are many other board, Raspberry Pi, uh, and so yeah, so the situation is actually sometimes very difficult to choose the right one, because it's already the Nano is already working on the robot, and changing the board will be difficult. Okay, the electronic parts has to be changed. If the electronics is not flexible, then we can't able to do anything, something like that. Yeah, Tushant, yeah, what will be the proper flow when considering or in series or any constraint embedded? Yeah, a proper flow in the sense, yeah, I will say, like, if you don't have any limit. Yeah,
That
yeah, Tushant, Tushant, yeah.
Yeah. So actually, I want to know, like, when we consider deep learning models, like they if it is a revolution convolution model, then they might consume a heavy
Yes.
amount of RAM. And if you want to still continue with those models on this constrained embedded system, considering like if we want to use, let's say, like scaled down version of our models, like small models, but still use on those embedded devices, then how to optimize in that manner, because we don't want to stick to one particular model, we want to use multiple models. So what would be the best way? Should we parallelly run those models, or
Yeah,
like that means how to
yeah,
optimize
yeah,
for
yeah,
that system?
I got it, Trushan. So, one of the things that I have done with Jetson series is that I think you know about the tensor RT, right? So, so if you have a CNN model, that can be optimized to that model itself can optimize to a specific hardware. So what NVIDIA are doing is that they are actually optimizing the deep learning model for their hardware. So they're doing that nicely, because for the people detection, no, the model itself, it's a big one, and in order to get the maximum performance from their device, even Nano, okay, Nano, they actually what they will do is they will convert, or they will optimize the model for the tensor RT. Okay, tensor RT is actually their library, their framework. If we convert the CNN model to tensor RT, it will work much better than the actual model. Okay, so this conversion will be happening automatically if you do the ROS deep learning. So from my understanding, in order to run the deep learning model, Jetson series is one of the best. um, they at least have this kind of library like Jetson Inference, which is already having a lot of trained models. So we don't need to depend, I mean, we don't need to train it, or we can like improve it if we want, and then we can optimize for tensor RT. And then what NVIDIA does is that this tensor RT model will be saved. Okay, then when we start playing with the model, okay, start playing in the sense, start detecting, the tensor RT model is loading instead of the actual model. Okay, so Jetson series is the only thing that I have seen, I mean, which is having a nice deep learning workflow. Okay, and there is Intel stick is the neural stick. They also having this, but not like Jetson series. So if you are planning to work with deep learning in an embedded, I will obviously prefer Xavier or Orin with the Jetson inference package. Okay, I think that will work perfectly. You can even work with the actual model, but this combination, that's why they created this stack, in order to optimize it. Okay, Trishant.
Yes, sir. Yeah, I did experiment it with TensorRT, converting first into ONNX and then the
Yeah, yeah,
.tensorRT file. Yeah, I was able to get a better
yeah.
throughput with that, but still I wish to know, like, if I use multiple models, because the thing is, like I'm not able to figure out if combining multiple models into single neural net is the ideal way, or like doing a parallel stream, because indirectly TensorRT will
Yeah,
use CUDA, like the
yeah.
context transfer, and for that it will send those particular things in batches. So the problem is if I run parallelly, then the GPU, when it is accessed by one particular pipeline, I won't be able to use
Okay.
another pipeline. So I that is the issue I'm struggling with
Okay,
in
so
that
you are
matter.
trying to run in parallelly, right? Like you are, okay, okay,
Yes.
okay. Oh, so
Actually, I just wish to know, because right now all the models are running
yeah,
like one by one. So the context is transferring from CPU to GPU, then back, revert the response
yeah.
one by one. But that's the thing. I want to know if there is a possibility where we can split the context either on hardware level, that doesn't seem plausible, but in software side at least, if we can have a upper level abstraction or something with which we can like
Uh,
improve the
uh,
efficiency, if I'm not
if
wrong.
we want to run multiple models at the same time, the difficulty that I'm seeing is obviously with the RAM. Like in the Jetson inference, I mean, if you are using the NVIDIA API for doing the detection uh, per model, okay, for a single model, there is an API for doing the detection, but that function itself take like 1 GB. Okay, that is the main function which is actually loading the TRT model into the RAM, and which will be taking 1 GB. And using that function, you can give the CUDA converted images into that, and it will do the detection. Okay, so if you want to do multiple model, what I will suggest is that, like, if you uh, if you create, I mean, I'm not sure about the name of the function, but if you keep on adding model, it will be at least taking 1 or 1.2 GB of RAM. Okay, and then you can read one image and you can pass to first detection function and the second detection function, something like in a serial manner. So in the software, I mean, software logic, maybe we can make it work by loading multiple models at the same time and processing serially. But if you are like giving the image concurrently to the all function, I don't know, it may be taking more GPU than expected, but serially may work. That is what I have done in the people detection. Even I was using one model, but if we have more RAM, maybe instead of people detection I can use maybe I mean people detection and car detection, for example. Load two models, TRT models, and pass one image first to people detection, and after that pass to the car detection, something like that. So what I'm trying to say is maybe the software logic may helps to save RAM and GPU. So that would happen in the Jetson series as well. If you are concurrently like passing images from four cameras to the model, then it is not possible. The RAM consumption will be very high. So I think for embedded system, some kind of logic will be helpful. Some kind of logic like this, like processing serially, may help. Yeah, that's what I'm thinking, Tushant.
Okay, sir. I'll check
Okay,
it
okay,
check it
okay.
out. Okay. Thank
Yeah,
you, sir.
Tejas is yeah. OpenVINO is an alternate of TensorRT. Yeah, OpenVINO. I will not say it's a replacement, but OpenVINO work. We already try with OpenVINO as well. So there are some problems with OpenVINO as well. Not problems, but we will not get that much performance in OpenVINO. And OpenVINO is a extension, right? We have to like plug into an USB. So USB one USB will be occupied, and yeah. But if you are working with Raspberry Pi and all, then in order to do deep learning, I think OpenVINO is. I mean, the neural stick is only one solution. OpenVINO library and neural stick, but I will prefer Jetson series. Jetson series compared to the neural stick. Yeah, but it can do something. I have tested it. Some models are optimized for neural stick, so that model will work. And heating is also an issue. Like we have to give proper cooling. Yeah, even if it is cased with a aluminum pack, but I think it can heat up after some time. Yeah, so yes. Okay, I think maybe next class we can start with ROS PCL. So I think you got an idea, right? In PCL also there is no much difference. It's like same stuff. Receiving point cloud, subscribing point cloud, and converting into PCL data type, and then doing the processing, and then publishing the process point cloud. But this time with the PCL, uh, it will take lot of RAM. Okay, depending on the size of PCL, it will take lot of RAM. This is where the situation are going to change. Like if you are planning to work with 3D perception, especially with PCL, your algorithm should be very what will I say, like very optimized. Okay, because if there is not much optimization happen, then you can't even run it. Okay, so again, one of the biggest challenge I will say in perception is the 3D perception. Okay, 3D perception, playing with millions of points. Okay, 3D points, and making sense out of it. Okay, not only like reading this point, the reading of these points from the depth sensor itself is, I mean, it's a hectic job for the CPU. Like it has to read from the IO, right? All this data, the bandwidth is, I mean, will be very high. So it has to read from the LiDAR or the depth sensor, and after reading, the PCL has to process the data, maybe filtering or segmentation. So these things will take lot of CPU and RAM. So in that case, I think GPU acceleration will help. Okay, so that's why I'm preferring Jetson series, because the point cloud processing, I think it can be like accelerated using CUDA. Okay, yes. Okay, so I think we can conclude for today. Okay, so now time for question. So if you have any question, let me know. Okay, yeah, time for question. Time for question. If you have any question, maybe other than yeah, maybe you can comment us. So next class, I think we can work on the PCL, and yeah, let me see. I can show you the YOLO object detection. Okay, let me see. Yeah. Oh, okay, Tejas. I hope I can work maybe tomorrow. Okay. Yeah. So I think yeah, tomorrow I will not. So tomorrow I can give the project list. So currently we covered the perception as well. So maybe I can include the perception, like the OpenCV and PCL as well in the project list. Not only gazebo simulation and autonomous navigation, I can put the perception. Okay. Yes. Thanks for yeah, mentioning that. Any more questions? The thing is, like after the travel, I was just settling down. So I think from this week, I mean, yeah, next week I will be like get more time with the class and also with the work. Yeah. Yes. Any more question? Can we conclude? If you have any question, just message me, okay, directly. And yes, so I will be uploading the session maybe today or tomorrow. Okay. Okay, guys. Good night. Thanks for attending. So see you next week. Tomorrow I will try to send the list of projects. Okay. Okay then. Bye everyone. Bye.